So implementation of the biasing, we just have seen all this biasing with the four sources, but I told you up front, this is really very unpractical. We have to make a practical solution. So this is our starting point. And the first thing is, of course, we are talking about structured design here. So I must find arguments for these sources, for the values of these sources. Now let's see what I can invent for arguments for the values of these sources. So this is the biased amplifier stage, and in this situation here we have the power delivered by the two current sources, and the other situation was the alternative, an alternative arrangement. You can see there are more arrangements, yes. And here in this case, the power is delivered by VGS and VDS. And we will now study the definition of the sources. We start with a definition of the output sources. So we are not going to bias the input of the transistor and then say, oh, and now this is what we measure at the output, so we have to apply the output. No, we start with the output. And why is that? Because the output determines the swing that we can have, the drive capability of our stage. And that is an important parameter for a transistor stage. How much current and voltage swing can we expect from such a stage? And not only that, it is also that it determines a lot of other parameters. But let's stick to this one first. Let's do VDS, this bias source. We have seen in our example that if the transistor is going to conduct fully, then it will, let's say its resistance will drop to a very low value, much lower than RL, then the voltage here will become minus VDS. So the output voltage can become minus VDS. So the excursion from the quiescent operating point, the maximum negative excursion from the quiescent operating point is set by this source. And if you are interested in the drive current, then you can say, well, if this transistor is fully conducting, then this can only cause a current here in this loop of VDS divided by RL. So the negative current, the negative current, the sink current of this device can be the VDS over RL. So it is set by VDS. Now let's go to the current. If the transistor is completely off, so for a negative input signal, then this current can only flow through the load, and the voltage will be IDS times RL. Of course, if this is 1 kilo ohm and this is 1 amp, it should be 1 kilovolt, and I think a CMOS 18 transistor can have neither 1 amp or 1 kilovolt. But let's say for this, we assume that we have a transistor that is not going to break down, that this value is the maximum value, because we are designing this on grounds of the need of the load. Let's say we want to have a certain maximum voltage or a maximum current, of course. So then this should be the peak excursion current from the operating point. That is the value of this course. And maybe a little bit more, but the best situation is that you have the situation that you really need is the maximum current that you have to deliver, the source current of the device. So you see, we have now design criterion for IDS and VDS. But in some cases, if this is your input stage and there's another stage, maybe you don't have to deliver that much. And then we see, and that is what we will see next time, that performance parameters of a bias MOS strongly depend on the operating point. So the operating current, so FT, GM, the noise performance, it's all very much depending on the operating current, on IDS. So it's common practice to start with the output port quantities definition and then apply the input that is necessary. But now the question is, how do we find those values? How do we find those values? Because the device equations can be extremely complex. So I will show you a method, a circuit for doing this. So basically we want this, and we want at the output the voltage to be 0 and no current. So in network theory, we have an element for that. It sets a condition setter, and we call it a nullator. But a nullator, it says here the voltage here should be 0 and there should be no current, but you always have to pair it with something that can satisfy the condition, and that is what we call a norator. And this together, this combination, and people who have done our bachelor course, they know this together is called a nullor. So this satisfies the condition, which means this will generate the voltage VGS and the current IGS, and you can just put it in SPICE and measure IGS and VGS and then convert it in voltages. But of course, SPICE doesn't have a nullor. Also in the first course, you find how you can make a model of a nullor, but let's say what is sufficient is a high gain voltage controlled voltage source. Let's say I have again a voltage controlled voltage source like this. This is the input terminals and this is the output terminals, and a gain of 1 million. And VGS needs to be 1 volt. Well, then here the voltage will be at the end only 1 microvolt. So that is almost 0. And here it will be no current. So this would be a setup that you could put in LT-SPICE, applying a voltage source and a current source, making a loop with a voltage controlled voltage source, measuring VGS and IGS, and then simply put them there after you have measured. Of course, you have to type in enough digits, and then you have your biased circuit, of course, only for this device and at the temperature at which you detected this. So it is still unpractical, but that is something I don't want to focus on now. In this constellation, in this setup, you see, we have already seen that there's no current through this voltage source and no current through this voltage source. So these are batteries, but they're delivering no current. So then we could also store the charge of the battery on the capacitor. So if zero frequency of the signal is not of interest, we can use AC coupling. And here, eliminate the voltage sources, and this current source will build up the voltage across this capacitor, and this current source will build up the voltage across that capacitor until the situation is completely satisfied. So that is called AC coupling, which is only possible, of course, if zero frequency is not of interest, and the bias current sources now are the active sources of the circuit. But we want the power supply. We want only one power supply. And what we now do is we redirect. This is another network theory theme. So the current was flowing from this node to this node. And now you let them go from this node to this node, and from this node to this node. So, and then you get this situation. And now you see I have two currents connected to the power supply. And if the power supply is large enough, then the voltages across these devices become positive, and the current is, you see, the direction of the branch current is following the plus and the minus sign of the voltage, which means now they are passive. And this one is the only one who has a current from minus to plus. So this one is the only one who is delivering power, and this one are becoming elements that dissipate power. So maybe later on, I can replace them with nonlinear resistors like another MOSFET, or I can put just resistors in it. We will discuss that later. But now I have something, I'm coming to a practical solution, of course. So the power supply is the only one now that is delivering current. But of course, this is still not very practical. Although I could maybe find implementations of these sources, you can imagine if the temperature changes a little bit and the leakage current in the gate increases a little bit, then the whole thing is not biased anymore in the correct operating point because the things don't match. So I have to apply a technique to make this a stable biasing. Now you can think of putting immediately resistors there. Well, that's what they do in most textbooks. But a resistor in parallel with the signal path also takes signal power. And maybe that's not what we want. So we want to put it in a wider perspective. And I want to show you a few things. And we are very interested in how you look upon this solution. So we are going to apply error reduction techniques for the reduction of the sensitivity for device characteristic and the reduction of the temperature sensitivity. that I discussed in the previous course in 9.4. And here you see examples of bias circuits that we have, that we want to present to you. And we now have a multiple select question for you on Brightspace, in which we ask you which techniques have been applied to achieve the stable biasing here. So here we have applied techniques: compensation, model-based biasing, brute force technique, negative feedback. So which words of here which do ring a bell if you look at these circuits? And maybe this is too difficult, maybe you never heard of brute force, but this is interesting for us to know, because the next lecture we will start with a discussion of this. So we will explain all these techniques in more detail, but first we want to know, where are you? What is the starting point for us that we have to discuss? Do you see somewhere that negative feedback is applied to get a stable biasing? Or do you see somewhere that we used an electronic self-inductance or whatever technique? So that is the question for us. Maybe it's a struggle for you to find the answer, but it is not for a mark. It is more for us to guide us through the lectures and say, okay, this is the thing we have to pay attention to.